Morning, welcome to today's session. So we'll continue with system of particles. We were looking at collisions in the last lecture, and we saw the definition of coefficient of restitution, right? We saw what is a perfectly inelastic collision where E becomes zero. So separation velocity becomes zero, whereas a perfectly elastic one is where E is equal to one, or separation velocity is equal to approach velocity in magnitude. Okay. And the general inelastic collision where E can be anything between 0 and 1. So let's continue from that point onwards today. So now we can have questions which are, based on the head-on collision for whatever given value of coefficient of restitution. But along with that, other things are also happening in the collision. So for example, we could have questions like this, where there is a combination of collision with other events happening, like a simple case of something sliding down an inclined plane. So basic application of work energy kind of thing. And then the collision situation. So this could be, for example, a smooth surface. And a particle E is released from rest over here. And then somewhere here it collides with another. And suppose given to us that this distance is h. So A is a particle of mass, let's say 2 kg, released from rest at h equal to 20 meters. Now A eventually makes an inelastic head-on collision with B, and mass of the particle B is 3 kilograms, with coefficient of restitution equal to 0.5. So we have to calculate find B's speed just after impact. Okay, so it's a very simple problem, two-part problem, where first we have to solve the motion of A as it comes sliding down the surface, the curved surface, onto the horizontal smooth part. And then you have to solve the collision. And for the collision, you can use the direct formula that we've discussed last time for head-on general inelastic collisions. Okay, to start working out this question, I'll just give you a recap of those formulae when we are discussing. Okay. Okay, so far I've got the answer from one person. So anyhow, let's understand what's happening here. By the time the particle is here, if it has a speed u, let's say, so u is equal to root 2 gh. We can just use work energy directly. So that's 20 meters per second. And then after the impact, let's say what happens after the impact is A's velocity becomes v1 and B's velocity becomes v2. So we can either go by the method of equations. So m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So in this case, 2 into u is equal to 2v1 plus 3v2, or so in this case that will become v2 minus v1 will become 0.5 times u. So we can go with the method of solving these two equations. You can see that so we just multiply this equation by 2 and add the 2. So we can see we'll get 5v2 according to this, right, is equal to 2 plus 1, 3u. So we should be getting v2 as 3 by 5u, or we should be getting B speed after the impact as 0.6 into 20. So that's 12 meters per second. So very good. That Deep, your answer was correct. Okay. So that is the one of the approaches you can take, or the other approach is you can directly use the formula if you remember it. But that's a little tricky. You have to make sure that you remember the formula. So V1 is M1 minus EM2 upon M1 plus M2 U1 plus 1 plus E into M2 upon M1 plus M2 U2. So if you remember this formula, then all the better. But you have to just make sure that you don't make a mistake while applying the formula. That's also equally important. So in this case, we'll get V1 as 2 minus 1.5 upon 2 plus 3 into 20. We get V2 as you can see 3 by 5 into 20. So 0.5 by 5 into 20. So that's this is also showing you that the separation velocity has become 10 meters per second, which is correct. And the momentum is 40 kg meter per second. Is also correct because the initial momentum was that much. So this is like a very basic example of application of the collision equations along with something else which is happening in the system. So that something else is the initial motion of the particle A, which is sliding down an irregular kind of inclined surface like this. So nothing very difficult in that also. We just use conservation of energy. Can't use kinematics because the path is not known, but can use conservation of energy because there's no friction involved. So just that common sense kind of approach. Okay. So this is the more typical type of question at the JEE level, where you have to use the equation of collisions or the formula of collisions for one part of the question. But obviously there's something else also happening in the question. And with advanced level questions, there can be more interesting things which are happening. So let's look at another example before we move on to two-dimensional collisions and also collisions of particles with surfaces today, which will be the main topic for today's lecture. But before that, let's look at another example of an application question. So these two blocks A and B are connected by a spring, and they're lying at rest with the spring at natural length on this frictionless surface. Okay. Whereas this block C is traveling with a speed V0 like this, and it makes a head-on impact with A. So given that A and B are of masses 2 kg and 3 kg respectively, with a spring of spring constant, let us say 40 newtons per centimeter attached between them and initially at rest. Sorry, at natural length. C is of mass 1 kg and moving at V0 equal to 12 centimeters per second and makes a perfectly elastic head-on collision with E. So we want to find velocities of A, B, and C just after the instant just after collision. Then the maximum compression of the spring after collision.
Sir?
Yes.
Sir, which collision is there? It will be given.
Sorry, which collision is there? Is given a perfectly elastic head-on collision.
No, sir. In all question, it will be given, no? Which
always the type of collision will have to be given, no? Whether it is perfectly elastic or inelastic, or the coefficient of restitution will be given. Understood, no?
Yes, sir. Yes.
Because without that information, we can't solve, no? Okay. Okay. We also have to find the maximum velocity for the block B after impact. So again, you have to basically break up this question into two parts. One is the collision between C and A. And you have to understand that because the spring has variable length now, So at the time when the impact happens, the spring is at natural length position. So it does not have any tension. So the spring does not play any role for the collision. The collision is like a collision between two blocks C and A. And the moment A starts moving, now the spring comes into action. So you can break it into a sequence of two events. One is an independent collision between C and A. And then the next part is that A has got some momentum. So it transfers momentum to B through the spring. So A plus B plus the spring become like a system, and you have to apply all the concepts of conservation principles to that system. But for the first event, C and A colliding, you don't have to take the spring and B into account because the spring does not have time to react yet. The collision happens very fast. It happens within a microsecond or two. So the spring does not have time to compress during that small interval of the collision. So spring doesn't come into action. So it is just like an independent collision between two blocks C and A for the collision part. Okay. So try to. Okay, I'll explain in detail. Okay, so again, what we'll see is that after the impact, immediately after the impact, what is happening is, let's say, this has a velocity v2, and we'll see that this will have velocity that we can prove from the formula. So for that, we can see that this one is having a mass of 1 kg, and this one is having a mass of 2 kg. Okay. So immediately after impact, this is what we'll get when we apply the formula. So minus of V0 by 3, or minus 4 centimeters per second. That will be C's velocity, but I'm more interested in A's velocity, which will be 2m1 upon m1 plus m2. So 2 by 3 of 12. So just after impact, this one's velocity will still be 0. The spring will still be at natural length. Okay, but A would have started moving the velocity like this. So this is just after impact. Okay, so the idea here is that during the impact, okay, the impulse by the spring on A or B is 0, because x is equal to 0 for the spring, and the time is very short. The collision time that's very short. Okay, so this is the important thing to understand. So that's why we can treat the collision like a separate event. Now, next, if we see some amount of time after the collision, what is happening? Then the story has again changed a bit. So C is, of course, going backwards. So C has come back somewhere here. A has moved forward, but B has also moved forward. But now let's say the spring has come to some compressed state. So it is applying tension. So at some point of time after collision, if we see, B's motion is accelerated. Okay. But A's motion is decelerated because of the spring force. So if the collision is happening at t equal to t, so this is just after collision. This is You can see that C has displaced by V1 into T. Okay, but A and B have displaced by different amounts because the spring is compressing. So sometime delta T after collision. This is what the diagram looks like. Okay, so if we picture, this is before impact. This is just after impact, and this is sometime after impact. So if we compare diagram 2 and 3, in that we can treat A plus B plus spring like a system to which we can apply the conservation principles. And that's what we'll do next. Yes, very good, Norman and Jay. Your answers were correct for the first part. Now see what conservation principles will apply between diagram 2 and 3 from just after the impact to a sufficient amount of time after impact when the spring is compressed by X. From diagram 2 to diagram 3, if we take A plus B plus the spring as a system, then there is conservation of linear momentum. Because as you can see in the diagram number 3, there is only internal force acting horizontally. Okay, external forces are 0. Net external force is 0. So we have mass of A into V2 initially is equal to mass of A into VA plus mass of B into VB. So we have in SI unit, it will be like this. And we have conservation of mechanical energy. So we have to make use of these two equations to solve for our other two quantities now. Other two quantities being for the B part, we need to calculate, or the second part, we need to calculate maximum compression of the spring. And for the third part, we need to calculate maximum value of B's velocity. Okay, so Harsh, let's understand where these equations come from. So if you look at this diagram, now the third one, you'll understand that once the collision between A and C is over, this becomes an independent system. Now, this system becomes independent. Okay, and on this system, there is no external force acting. Once the collision is over, okay, after that, there's no external force happening because the only type of force acting is the internal spring force. It cancels an action reaction pair. No? So this system's momentum is conserved and there's no non-conservative force because no friction on the ground. So no dissipation of energy also. So mechanical energy is also conserved. So just after impact, how much is the linear momentum? A has this much linear momentum and B has 0. So the total linear momentum is this much. And a bit of time after impact, if their velocities are VA and VB, the linear momentum of the system is this much. Is it clear now? Equation number 1?
Yes, sir.
Okay. And similarly, just after impact, A's kinetic energy is this much, but B's kinetic energy is 0. The spring's potential energy is 0 because just after impact, this is the state. In the diagram 2, you can see A has velocity, B is at rest, the spring is at natural length. So the total energy of the system is just this much. But a bit of time after impact, the energy has changed to this, where A and B have some kinetic energy plus the spring has some potential energy. So this energy is redistributing energy on the right hand side, while the total energy is remaining conserved. Okay, now equations 1 and 2 are clear now?
Yes, sir.
So when we convert this to values, you will see this will become V2, which was 8 into 10 raised power minus 2 whole square. That should be equal to VA square plus 3 by 2 VB square plus, now K was 50. So this will become 25 into 10 raised power minus 2 in SI unit X square. So this is our second equation. Now we have to solve equation 1 and 2 for these two specific values. Okay. This thing, maximum compression and maximum speed of B. So now if you look at this very carefully, you'll realize that equation 1 and 2 have 3 variables, VA, VB, and X. So we cannot solve them directly because we have only 2 equations. But there is also a specific condition for which we are solving. So the specific condition in part 2 is that we have to find maximum X, maximum compression. So when the compression reaches a maximum value, there is a specific condition on A and B's velocity. Can you tell me what that is? So I'll just give you a hint. Initially, BA is more than BB, na? Because A starts moving, B takes some time to pick up velocity, na? Because it has to accelerate from 0. So initially, when V is greater than BB, what is happening? E is approaching B. So the spring is compressing. Okay. But after some time, eventually, because A is decelerating because of the spring force, you can see in the above diagram, the spring force is making A decelerate and B is accelerating. So VA becomes less than B. So at that point of time, what happens? B is separating from A. So the distance between them is increasing. So at that point of time, what is happening? The spring is relaxing back. Okay. So A's velocity with respect to time is actually decreasing like this. Whereas A's velocity is decreasing. Whereas if you look at B's velocity, it is increasing with respect to time from 0. And at some point of time, the velocities are equal. So that is when the spring will have the maximum compression. Are you clear on this point?
Yes, sir.
Because like just imagine you're sitting on A. So initially it will look like B is coming closer to you because they are approaching each other. But after some time, B is again going back away from you. So at the moment when B came closest to you, it should look like it's come to rest momentarily. So that means relative velocity should be 0. That means in the ground frame, what should be the velocity? It should be equal. So at some instant in between, VA is equal to VB momentarily. So that is when the spring is at maximum compression. Because A and B are closest. Okay, so that is when their relative velocity is 0. Okay, so we have to solve equation 1 and 2 for this condition now. So next what we have to do is solve equation 1 and 2 for the condition that x is equal to its maximum value when at the instant when V is equal to VB, or the relative velocity is 0 between them. Okay. So let's do the solving now. So from equation 1, VA will be equal to VB at the instant when it becomes how much? So substitute VA equal to VB in the above equation. So 5 VA or 5 VB, whatever, is 16 into 10 raised by minus 2. Okay. Or we can just write it like this, that 2 times V naught. Or let's write it like this only, it doesn't matter. So VA will become 16 by 5 or 3.2 centimeters per second. Equal to VB. Now substitute this in equation 2. Okay. So we have 8 centimeters per second square will become 1 plus 3 by 2 into 3.2 into 10 raised by minus 2 whole square plus 25 into 10 raised by minus 2 into x's maximum value square. So from this we will calculate the maximum value of x. So this will become the maximum compression. So this is a very important concept to understand over here, that the spring has maximum compression at the instant when VA is equal to VB, or the relative velocity of A with respect to B is 0. Okay, now let's come to the third part. So in the third part, what we have to do is we have to find the maximum speed for B. Okay. So again, for that, what we'll understand is that as long as the spring is compressed, what is happening to B is that it is getting pushed, it's getting accelerated. Okay. But eventually, after some time, the spring for a moment reaches the natural length. And after that, the spring again extends, because it's attached to both the blocks. So that point of time, B will start to decelerate. So that means when is B having the maximum velocity? It is having the maximum velocity at this instant. VB is maximum. At this point of time, the velocity is increasing. After this, the velocity is again decreasing. Okay. So B has the maximum speed at an instant when x is equal to 0 for the spring. Or another way to understand it is that the potential energy of the spring becomes 0. So kinetic energy of the system becomes maximum. So equation 1 will remain the same, that so we have 2VA plus 3VB is 16 into 10 raised to minus 2 meters per second. Okay. But equation 2, in that we will put x equal to 0. So VB has its maximum value. So we'll have VA square plus 3 by 2 VB square is equal to this kind of equation. Or if we just solve these two now, this equation can be written as and this equation can be written as So if we just divide the equations, we can see that and to that you can compare this equation. Now to compare these two equations, you can just multiply these equations by 2 and add them. So we can see that VA will get cancelled. So we'll get 5 VB is equal to 32 into 10 raised by minus 2. So VB will be, okay, this will be the maximum speed of B. Okay. And again, that maximum speed will just exist for an instant, because after that, again, the spring extends, so B starts to decelerate. So actually the spring oscillates from compression to extension, and back like that. And as it oscillates, the speeds of A and B are continuously increasing and decreasing. But at the instant when B is having maximum speed, the spring will be at natural length, and the speed of B at that moment will be 6.4 into 10 raised by minus 2 meters per second, or 6.4 centimeters per second. Okay, so I'll just take you to the top of this here. Understand this in detail. You just go through this once. So this type of question will take a bit of practice and experience in problem solving. Okay. This chapter has like very good collection of questions and very large number of collections in H.C. Verma itself. Okay, so by the time you complete H.C. Verma in system of particles, I think something like 90% of your job for JEE is almost done. And by the time you complete your module, you have done more than enough questions required for JEE level. Okay, so there is no shortage of questions and practice, just that you have to put the time and energy into it. Okay, so let's move on. Hope this question was clear to all of you. So there are quite a few questions of this type in HC Verma, which you can practice out and you can discuss the details, doubts and all in the next lecture. So you can perfect the technique and problem solving method for these. Okay. Now next we'll move on to the other type of collision. So in the second category of collisions, we saw head-on collisions. So far we have seen head-on or one-dimensional collisions. Now next we will see collision of a particle with a rigid surface. Like for example, a ball bouncing on the floor, or a projectile going and hitting a wall or some surface like that and bouncing back from it. So those are examples of collision of a body or a particle with a rigid surface. Let's see how we'll apply the collision principles for that. So what we mean by a rigid surface is that the surface is fixed. And of course, fixed to what? It is fixed to the earth or fixed to the ground. So that means it has infinite mass because it is part of the earth. Okay. So that's how we have to visualize it. So a rigid surface is a fixed surface. Okay. Means fixed to the earth. So you have to treat the earth like an infinite mass. Okay. Example, a floor or a wall, like that. So to understand what happens here, let's go back to head-on collision first, and let's look at what happens when a particle of mass m moving with a velocity, let's say v0, goes and collides with a heavier object, let's say like this, but head-on collision of mass capital M at rest. Okay. So if it makes a head-on impact with a coefficient of restitution equal to E, then we can see what happens immediately after the impact is that we are assuming that M is less than capital M. So V1 will become M1 minus EM2 divided by M1 plus M2 times V0. And you can see this will be a negative quantity because M is less than capital M. So assuming M is less than E times capital M also. Okay. So this will have a return velocity like this because it will be negative. Okay. And this one will have a velocity like this, 1 plus E times M1 upon M1 plus M2. Okay. Now in this, if we apply the limit that capital M is very large compared to small m. Okay. So for example, capital M might be something like literally millions of kilos and small m might be few grams. So you can see that in that case, m by capital M is of the order of magnitude of 10 raised power minus 9. So you can say that m by m is very small compared to 1. So in the above equations now, if we apply that limit, okay. Or let's take the case first of perfectly elastic collision. Just make life easier for a moment. Then we'll come back to the inelastic case also. So this becomes M1 minus M2 upon M1 plus M2. And this becomes 2 times M1 upon M1 plus M2. So on this, when we apply the approximation, okay, so what we'll do is we'll multiply divide by capital M. So this will become okay. So we are dividing by capital M in the numerator and denominator. Okay. And then we are applying the condition that M by M is negligible compared to 1. Okay. So we can say that this V1 becomes approximately equal to minus V0. And V2, which was 2M upon M1 plus M2, by the same process, it becomes like this. So V2 tends to 0. So that is what happens if the second object is very, very heavy compared to the first one. The second object will tend to remain at rest in a perfectly elastic collision, and the first one will recoil with a speed V0. Okay. So that is what happens, for example, when a particle is bouncing off the earth in perfectly elastic collision. This is the floor, and a particle starts from here. So if it impacts with the velocity V0, then immediately after impact, just after impact, and just before impact, provided the collision is perfectly elastic. Okay. So basically what you're saying is that you're treating the floor as if it's part of the Earth's surface. So mass of the Earth is tending to infinity. And that particle is doing this. So after impact, the Earth remains at rest, but it has negligible velocity. And the particle recoils at separation velocity equal to approach velocity, equal to the velocity of impact, which is V0. Okay. So I'll just minimize this and go through it from the mathematical derivation above also, and then the physical explanation of it below. Okay, so anyway, we'll have to write it in two parts. So let's.
Sir, 1 minute.
Yeah.
Done, sir.
Okay.
Sir,
Yes.
sir, could you just show the last line?
Yeah, sure. This part?
Yes, sir.
Sir, this is which type of collision?
Sorry, come again, beta.
Sir, this is which type of collision?
So this is a collision between a rigid surface and a body. Okay. We are developing the theory for that. So how we treat it. So for example, if an object is colliding with the Earth's surface, so it's basically colliding with the floor and it bounces off the floor like this in a perfect elastic collision, what will happen? It will tend to have the same velocities magnitude after impact as it had before impact. And what is the reason for that? The reason for that I've explained in the explanation above. Understood the point?
Yes, sir.
Okay, so we will generalize this more now. Okay, so what we'll generalize it is like this. So if we have what is called a normal impact. So normal means perpendicular. Perpendicular normal impact of a particle with a fixed rigid surface like the floor. Okay. So imagine the particle is not in accelerated motion. So this need not be a vertical motion. It could be like one of the coins of the carom board going and hitting the side of the carom board. Okay. So when this hits also, it hits with a velocity v naught. But the direction of the velocity is perpendicular to the surface. This angle is 90 degrees. So that is what is meant by a normal impact. The velocities, the impact velocity's direction is perpendicular to the surface. So in this case, we say that the approach velocity is equal to v naught only, because the approach velocity is the rate at which the distance between the particle and the surface is decreasing. Okay. So during the impact, what happens is that the particle experiences a normal impulse, a collision impulse, which is going to be along this vertical line only, or along this perpendicular line only. So that is why it cannot gain any momentum in the tangential direction. The normal impulse it experiences, let's say n delta t, or the collision impulse, okay, the impact force impulse, which is in the direction, which is normal. So it is called the normal impulse. Okay. So as a result of that, the particle's momentum immediately after collision will become like this, let's say. So it will remain perpendicular. So this is just after the impact. And in this case, you can see that the separation velocity is equal to V. So V should become equal to E times V naught, where E is the coefficient of restitution. Okay. So also in this case, you can see that when it is perfectly elastic, the V will be equal to V naught in magnitude, only the direction gets reversed. So there is conservation of kinetic energy, and separation velocity is equal to approach velocity. Whereas when E is less than 1, there is loss of kinetic energy. And when E is equal to 0, the particle completely sticks to the surface. So the separation velocity becomes 0. So we'll see that depending on the value of E, again, you have the extreme cases of perfectly elastic when E is 1, or perfectly inelastic when E is 0, or the in-between situation of inelastic collision, partially inelastic when E is between 0 and 1. So this is the first situation of collision of a particle with a fixed rigid surface, that is the normal impact. Okay, when the direction of the velocity is perpendicular. So perpendicular or normal impact. Okay, so write this down. Next, we will see the oblique impact when the particle comes and hits at an angle.
That means we can directly find the velocity, final velocity.
Okay, so this is clear. Let's look at a quick question based on this now. So again, these are very common questions at JEE Mains type of level. So let's say you have something like a tennis ball. Now you drop it. So initial velocity is 0. From a height of initial height h0 of, let's say, 20 meters above the ground, and you take g as 10 meters per second square. Now suppose it makes a collision with a coefficient of restitution of 0.6. So you have to find V0, the impact velocity for the first impact. V1, the velocity just after the first impact. H1, the maximum height after the first bounce. Similarly, H2, maximum height after the second bounce. Okay. And you will see a pattern, and from that you can figure out what is the maximum height after the nth bounce. Okay, so just try this out, people. Okay, very good. That's correct, Deep. So you will see that it becomes a geometrical progression, right? The heights, it becomes like h naught upon e to the power n, e to the power 2n. So it actually helps if we do this type of question parametrically. That is in terms of the parameters rather than their values. So we'll see that when we drop this object from a height of h naught, starting from rest. So as it makes the impact, for the first impact, the impact velocity v naught will be root 2g h naught, which in this case is 20 meters per second. So immediately after that impact, it will have a velocity of v1, which will be e times v naught. So in this case, it will become 12 meters per second. Okay. So then thereafter, what will happen is it will go up to a certain height and return back. Now this height will be less because here again v will become 0. So h1 will be equal to v1 square by 2g. So see, it will be equal to e v naught whole square by 2g. So it will be e square times v naught square by 2g. Okay. And if you connect this relation here, you can see that h1 will become e square times h naught. So in this case, that will become 0.36 times 20. So it becomes 7.2 meters. Now again, when it collides next time, it will have an impact velocity of v1. And after impact, the velocity will, let's say, become v2. Sorry, v2. So v2 will be equal to e times v1. So like v1 was e times v naught. This is e square times v naught. The next time it collides, v3 will be e times v2 or e cube times v naught. Okay. So the first bounce, then second bounce like this. After the nth bounce, the velocity will be e to the power n times v naught. Okay. And like that, between the first and second bounce, the maximum height is e square times h naught. Between the second and third, the maximum height will be e to the power 4 h naught. Between the third and fourth, it will be e to the power 6 times h naught. And like that, after the nth bounce, maximum height will be e to the power 2n times h naught. Okay. So this will be 0.36 into 7.2. So that kind of progression it will form. Okay, so people hope this is clear.
Sir,
Yeah,
sir, could you just show the last line?
yeah.
Done, sir.
Okay. Now next we'll look at the oblique collision of a particle with a rigid surface. Okay, so again imagine that this is like the wall of your carom table or one of the side walls of a snooker or pool table, and you have that spherical pool ball or carom coin, which is disc shape, whichever, but it's coming and impacting like this. So it's making an impact obliquely, okay, such that if I draw the normal, the angle at which it is to the normal is this theta. In fact, let's take it as theta naught. Okay. So you can also think of it like an angle of incidence. This is the normal to the wall or the surface. So this angle here, this is the angle of incidence. Okay. Now, as this comes in contact, the collision impulse that will act on the body will again be just in the normal direction. It will not have any perpendicular component, or it will not have any tangential component. So during contact, this one will experience an impulse in this direction, and this one, the wall, will experience an equal and opposite impulse in this direction. Okay. So this is the normal impact impulse or collision impulse. So you can see that that is along the normal axis. So the tangential component of momentum will be conserved. The collision impulse is along the normal axis. Therefore, the tangential component of momentum which you will see in the diagram, if the mass of the colliding particle is m, it is equal to mv0 sine theta naught. This is conserved. So as a result of that, after impact, so just before impact, when the particle is here, it has a momentum in this direction, which you can break into the two components. Okay, so this is the normal component. and this is the tangential component. So now just after impact, and the particle came in like this, and after impact it went off like this. So if it has a velocity v like this, this angle is theta. Now you can see this is the tangential component, b sine theta, and this is the normal component, v cos theta. So the tangential component of momentum is conserved. That means mv sine theta is equal to mv naught sine theta. So that gives us the first equation, that v sine theta is equal to v naught sine theta. Okay. And we can also see that in this diagram, the approach velocity is v naught cos theta naught. That is the normal or perpendicular component. And in this diagram, we can see that this separation velocity, as it goes along like this, the separation velocity is again the normal component. After impact. Okay. So the relationship between the approach velocity and the separation velocity will again come from coefficient of restitution. And that will give us our second equation. And that's how we solve the problem completely, that we have two equations and two variables. So v cos theta becomes E times v naught cos theta naught. That becomes our second equation, where again E is equal to 1 for perfectly elastic. E is between 0 and 1 for inelastic or partially inelastic, and E is equal to 0 for perfectly inelastic. So just make a note down of these equations.
Done, sir.
Done, understood. Okay, so just to wind this up, you'll see that when we take the case of the perfectly elastic collision, again, it is a situation which looks like a mirror image because theta naught becomes equal to theta. So seeing the two equations in isolation, you have V sine theta is equal to V naught sine theta naught. Okay. And V cos theta after impact is equal to E times V naught cos theta. Okay. So for a perfectly elastic collision, when you take E is equal to 1, you get this equation remains the same, but the second equation has unity side. Okay. Equation. So if you square and add them, you can see that V square becomes V naught square, or the magnitude of this velocity is equal to the. Okay. So kinetic energy is conserved. Okay. So this you will get if you square and add the equations. And if you divide the equations, you get that theta is equal to theta naught. So this is like a reflection. Angle of incidence is equal to angle of reflection, that kind of situation. Okay. So we can always visualize a perfectly elastic oblique collision as if the colliding particle is reflecting off with the same angle of reflection as the angle of incidence and at the same speed as the impact speed. So if E is equal to 1, then after impact, go at a speed equal to V naught. And such that this angle is equal to this angle. Whereas if we take the case of E equal to 0, so solving these two now tells you that V is equal to V naught sine theta naught and theta becomes equal to pi by 2. So the particle sticks, okay, to the surface, slipping tangentially at V equal to V naught sine theta. So this is how that situation looks. Now immediately after impact, it's stuck here and moving with this V. So this angle becomes 90. So this is also a case where you can see that separation velocity becomes 0 and the loss of kinetic energy is maximum. And for any general in-between case, what will happen is that theta will become greater than theta naught, but less than pi by 2. And V will be less than V naught, but greater than V naught sine theta naught. Okay, so this is the complete description of collision of a particle with a rigid surface. Okay, both normal impact and oblique impact, and the cases of elastic or inelastic collisions or perfectly inelastic, etc. All the cases. Okay, so now the next thing we will be discussing in collisions in the following lecture that we come to will be the oblique collision of two bodies, or what we call the two-dimensional collisions. Okay, but once you have a bit of experience in solving things related to these two types of collisions, the one-dimensional collision and what we have discussed today, collision of a particle with a rigid surface, you'll see that what follows for oblique collision of two particles becomes like a natural continuation of this. So it will be easy to understand. Okay. So that's it for today's session, people. We'll pick up from here onwards in the next lecture. So we'll start with oblique collision of two particles in the next lecture. We'll do questions related to collisions and momentum conservation situations and all. So start like working out, try to like finish most of the exercise of HC Verma in the coming week, okay, so that you're in a good position with respect to your problem solving and assignment of system of particles. And as you complete more and more questions of HC Verma, you can start doing questions from the module. So for example, at this stage, you can do questions up to one-dimensional collisions, or even the part before that, conservation of linear momentum, center of mass, motion of center of mass, all these things from the module also. Okay. Anyhow, so that's it for today's session, people. Wish you all the best.